Hello, and welcome to class number 28 of Physics 218. So last time we discussed an analogy between vectors in 3D and wave functions. So we learned some important things about the stationary states size of n of an infinite square well. So we learned that the stationary states form a basis, that the stationary states are orthogonal with something like the dot product, the inner product, defined in terms of an integral. So the fact that there's a basis, that they form a basis and they're orthogonal, and that the stationary states are normalized, you will often hear the language of the stationary states form an orthonormal basis, so orthogonal plus normalized, orthonormal, and that's language you'll use more in 421. And then we talked about how any general or arbitrary wave function, which I'm just going to use f of x here, can be expanded as a sum of the stationary states. So what I want to talk about today is a few things. I'd like to talk about time evolution for an arbitrary initial wave function. So if I have the wave function at time t equals 0, whatever it is, how do I find what the wave function is at later times? I want to talk about the physical interpretation of the expansion coefficients C sub n. And then we'll introduce some concepts about operators, eigenvalues, and eigenfunctions. When we come back on Monday, we'll have, I think, some loose ends to tie up with Chapter 3. I want to talk about sort of summarizing all of the principles of quantum mechanics that we have been introduced to over the last few classes, to try to give you a better sense of the big picture. And so that'll be for Monday. I recognize you probably have lots of questions about the really cool but also challenging ideas we've introduced in the last couple of classes. So please fire away at me, and I will try to get to as many as I can on Monday. So in response to one student's question about sort of where these ideas we talked about just came from and why we ought to care about them, I do want to sort of bring up one thing that I didn't mention last time, which is that pretty much all of the concepts we discussed in terms of basis functions really applies to classical waves as well. And frankly, it's an idea that you'll encounter in other branches of physics. So let me be really concrete about this. So you're probably really familiar from Physics 217 with the standing waves on a string. So let me imagine, right, that I set up a situation where I have a string that's clamped, that's fixed at both ends. So, maybe you imagine plucking a guitar or a violin string, right? So, I don't play a string instrument, but maybe you do, or somebody in your family plays guitar or something like that. But you can probably just imagine the situation. If I have, here's my guitar string. If I want to get it to make some sound, I could go and pluck it, and then let it vibrate. Well, if I pluck a guitar string, right, you know, right, that you know what the standing waves on this look like, right? The standing waves are exactly the same shape as our stationary state wave functions, right? Because they have to obey the same boundary condition that here the string is clamped, at zero displacement at both ends. Now, if I erase this for a second, right, you know that if you go and pluck this thing, right, you're probably not gonna be able to sort of shape the string to exactly be in the fundamental, right? And you know how the fundamental vibrates from 217. You're almost definitely not going, no matter how good of a guitar player you are, I pretty much guarantee you're not going to be able to pluck the string into like the first harmonic either, right? You just can't make that shape. Instead, when you pluck the guitar string, what you're likely to get is a shape more like sort of this kind of tent, right? If I just pick it up if I just sort of pick it up in the middle, I could imagine if I just pull the string out with my fingers, I can probably get a shape kind of like this. Here's the thing, right? This can be expressed as a sum of the various standing waves, just like we talked about with like the expansion of the tent wave function in terms of the stationary states, right? So this is of standing right, and why this is really cool is if you think about the sound, right? You know from 217 that each of the standing waves oscillates vibrates with a different frequency. If you go and you pluck a guitar string, you know you're not gonna you're gonna get a beautiful, assuming you have a goodish guitar, right? You're gonna get a beautiful and somewhat complex sound. You don't just get the sort of beep, sort of the very, that's not it, but you don't get this very flat tone you get if you just play a sine wave. And the reason you don't, right, is because whenever you pluck a string, and you put it in this shape, you're exciting not just the fundamental, but all of the higher harmonics, or in musical acoustics terms, what you call the overtones of the string. So in a real sense, like the Fourier ideas we talked about last time really do manifest themselves in a classical context, and frankly, if musical instruments only sounded the fundamental, we wouldn't have music the way I think we tend to appreciate it. So I wanted to mention that because the really abstract ideas we talked about last time do come up in classical physics as well, and frankly, there are some folks and some universities where prior to a course in quantum physics like the one you're in, one sort of does a much deeper study of classical waves, including sort of these sorts of concepts. But that's neither here nor there. Okay, so we're now finally in a position to completely answer the question I posed for the first time several classes ago, which is the general case of time evolution. Namely, the question is, if I know the wave function at some initial time equals 0, what is the wave function at all subsequent times? We can answer this question in the following way now that we've learned how to expand an arbitrary wave function in terms of stationary states. So the answer is, expand initial wave function in stationary states. So namely, you do whatever you need to do the integrals to calculate the expansion coefficients, right, in the sum. So summing over n, Cn psi and x, where the C sub n are expansion coefficients. These are our stationary states. But the key thing is that we know how each of the stationary states time evolves. right? Time right? Each of the stationary states in the sum, time evolves according to that e to the minus I e sub n t over h bar, a complex exponential factor, right? So this gives psi of x t, right? Ends up being a sum over n, c sub n, psi sub n x. Now e to the minus I e n t over h bar, because we know how the stationary states time evolve. So the overall behavior of the wave function, again, just means that we break it down and then each of the stationary states evolves in its own way. I'm going to now cut to my computer so that I can show you some movies for time evolution for two cases. So I want to show you the box wave function and how that time evolves. And then I also, just for kicks, I want to also show you what happens after a position measurement. So if I start with my wave function as a really sharp spike after an initial, let's say I measured the position to be somewhere at t equals 0, how does the wave function subsequently evolve? So hi everybody, I just wanted to show you this movie that I made showing the time evolution of an arbitrary initial wave function in an infinite square well. So the wave function I wanted to show you was that box wave function. This being a computer simulation, I've only been able to retain a finite number of terms here, which is why you see a little bit of the ringing here, but it's basically a flat wave function in the middle and dropping off to 0 at the edges of the well here and here. So let's watch what happens. So again, the way this code works is that I broke this initial wave function and down and wrote it as a sum of the stationary states. I time evolved each of the stationary states and then sort of add it all up together. So let's see what happens. So let's see if you can see that. And you get this sort of weird and wacky behavior where that initial nearly flat wave function starts spreading out and doing some really wacky things. So this plays for a little bit. I'll post the whole video to YouTube, I think, so that you can play it for yourself. Maybe what I'll do is I'll pause it here. And I'll just step it through. So you can. So we're at 0, and then as I sort of advance time forward, you can sort of see stuff coming in, and now you get this sort of wonky oscillating behavior. So that's that one. I want to show you one other example, which is connected to the idea of, well, what if we made a position measurement? So for this, I've set the initial wave function to be a really, really sharp spike. Now this isn't quite a position eigenfunction here, right, because that would require an infinitely narrow spike, which I can't really do computationally, at least not in a straightforward way. This video actually took a while to generate. But once again, if I sort of march time forward, you can see that really sharp initial spike quite quickly begins to spread out. So here, if you look at the wave function or at the probability density, you can see that. Let me just see if I can step it. Yeah, maybe I can drag this control out of the way and just step. And what you see, right, is, so if I rewind and step forward, what you can see is the initial really sharply spiked wave function just spreads out, and we get quite quickly this sort of oscillating behavior again. what I might point out is that what you end up with is sort of, on average, if you wait long enough, this sort of oscillating wave function probability density basically you end up getting a nearly sort of time averaged uniform probability of detecting your particle somewhere within the well um, after you started off, right? Because if you think about this is the initial, if I rewind this here, the initial state has a very small position uncertainty, which means it has a very high momentum uncertainty, and that it shouldn't be too surprising that because of the high uncertainty and momentum, you wait long enough, essentially you have very little, you basically have no idea where the particle is within the well. So I'll post these videos so that you can play them for yourselves. So I want to turn now to thinking more about how to physically interpret these expansion coefficients C sub n. As a reminder, right, if I have some arbitrary wave function, let me call it f here, the n expansion coefficient is given by this inner product, right? It's the integral of psi n star, the n stationary state, multiplying my arbitrary wave function from 0 to L. I now have a clicker question for you to think about, just so that we get warmed up thinking about this sort of thing. We'll take a moment to think about it and then come back together. Okay, so hopefully you had a chance to think about this, right? And so the expansion coefficient C2, right, is going to be given by the product of our n equals 2 stationary state and this arbitrary wave function, this box, right? Well, this wave function is constant 1 everywhere between 0 and L, so the product is just this, right? But notice, right, because of the symmetry across the middle of the well, if I integrate this product, right, between 0 and L, I'm going to have an equal amount of area that's positive here as negative down here. So this means that in this case, C2 equals 0 by symmetry. And so hopefully you can see how that works itself out geometrically. This kind of trick for thinking about symmetry and what that does to a calculation is a very useful one. So I want to say more now about how to physically interpret these expansion coefficients. So the first thing that I want to mention is sort of might help you get the picture, is that the C sub n is a measure of the psi sub n-ness right, of our arbitrary wave function. And so what do I mean by sort of psi sub n-ness, right? It's basically how much of this arbitrary wave function can I describe with that stationary state. So maybe what helps is a little bit to look at a concrete example, right? So I want to turn to the tent that we looked at in a simulation last time. So here's my tent arbitrary wave function, right? So if I kind of stare at this, right, it's not sinusoidal, but it basically has one bump in the middle, right? We probably would expect that this has a lot of psi 1-ness, right? Because we know that psi 1 has, a shape that's just got one bump in the middle, kind of looks similar. And that's in fact the case, right? So here's by slide 1. So this has a lot of psi 1. Yes, so qualitatively speaking, right, and to be really specific, right, it has C1 turns out to be for root 6 over pi squared, which is pretty close to what it turns out to be, 0.9927. So, in fact, most of the this is the biggest contributor to this overall arbitrary wave function. Now it turns out that that C2 equals 0, and it turns out to be based on a symmetry argument, like what we just talked about. But there's also contributions from the other stationary states, right? So psi 3 we know looks like this, but it's got some of the, it's got a little bit, and it's harder to see. Here it's got a little bit of sort of 3 bumpness. C3 turns out to be minus 4 root 6 over 9 pi squared. And so that turns out to be a lot smaller, about minus 0.1, and let me just get that number for you. And that turns out to be minus 0.1103.